You already know what a wormhole is supposed to be: a tunnel through space-time, a shortcut. 2 points in the universe connected by a passage that bypasses the normal geometry of space, so that a journey of 1 billion light-years becomes a walk through a corridor. You know this because it is in every science fiction film ever made. And because of that, most people assume physicists invented the concept to make movies interesting. They did not. Wormholes emerged directly from Einstein's equations of general relativity, not as speculation, as mathematical solutions. The same equations that correctly predict black holes, gravitational waves, and the bending of starlight around the sun also produce wormholes. The universe's own equations keep generating them. The problem is what the equations also say about them. Some collapse instantly. Some require matter with properties that may not exist. Some are traversable in only one direction. And some, the strangest ones, suggest that every entangled particle in the universe is already connected by one right now. Here is every type physicists have seriously theorized, and what the mathematics actually says about each of them. 1. The Einstein-Rosen bridge. The original, which immediately kills you. The story starts in 1935 in a single paper published by Albert Einstein and Nathan Rosen in the journal Physical Review. Einstein and Rosen were not trying to build a shortcut through space. They were studying the mathematics of black holes, specifically the Schwarzschild solution, which describes the space-time geometry around a non-rotating, uncharged mass. When they extended the solution to its full mathematical range, they found something unexpected. The equations described not one region of space, but two, and between them, a bridge. A throat connecting two separate regions of space-time, or two separate universes, through a single point. They called it a bridge. John Archibald Wheeler later named it a wormhole, using the analogy of a worm boring through an apple, traveling through the interior of the apple rather than across its surface. There is one immediate and insurmountable problem with the Einstein-Rosen bridge. It is not traversable. The throat is not stable. From the moment it forms, it collapses, faster than the speed of light. No signal, no particle, no information of any kind can pass from one end to the other before the bridge pinches shut. The mathematics is unambiguous. The collapse happens at the event horizon. Anything attempting to cross is simply crushed as the throat closes around it. The Einstein-Rosen bridge is not a tunnel. It is a description of what the interior of a black hole connects to. And the answer is another region of space-time that nothing can reach. Mathematically beautiful, physically unusable. 2. The Morris-Thorne wormhole. The one that started everything. For 50 years after Einstein and Rosen, the wormhole was considered a mathematical curiosity with no physical relevance. That changed in 1988, when physicists Michael Morris and Kip Thorne published a paper in the American Journal of Physics asking a specific and previously unasked question. If you wanted to design a traversable wormhole, what properties would it need to have? They worked the problem backward. Rather than starting with a matter distribution and calculating the resulting geometry, they started with a geometry, specifically, a wormhole throat that stays open, connects two regions of spacetime, and allows a human being to pass through without being killed by tidal forces, and calculated what matter distribution would be required to produce it. The answer was exotic matter. Specifically, matter with negative energy density, material that pushes outward on spacetime rather than pulling it inward, creating the repulsive effect needed to hold the throat open against the gravitational tendency to collapse. This is not antimatter, which is simply normal matter with opposite charge. Exotic matter, as defined by Morris and Thorne, would need to have a negative energy density as measured by any observer traveling through it, a property that violates the classical energy conditions of general relativity. Does exotic matter exist? In a strictly classical sense, almost certainly not in the quantities required. But quantum mechanics offers a partial answer. The Casimir effect, the measurable attractive force between two uncharged parallel conducting plates in vacuum, arising from quantum vacuum fluctuations, produces a region of negative energy density between the plates. This was experimentally confirmed by physicist Steve Lamoureux in 1997, measuring the force to within 5% of the theoretical prediction. The Casimir effect produces negative energy density. Just not enough of it, and not in the right configuration, to hold open any macroscopically traversable wormhole. The physics is real. The engineering gap is enormous. The Morris-Thorne wormhole established that traversable wormholes are not forbidden by general relativity. They are permitted if exotic matter exists in sufficient quantities and the right arrangements. Whether that condition is met anywhere in the universe is unknown. 3. The Lorentzian wormhole. The traveler and the time machine. A Lorentzian wormhole is the broad class of traversable wormhole solutions in general relativity, named for the Lorentzian signature of spacetime, the mathematical description of one time dimension and three spatial dimensions that characterizes the universe we experience. What separates Lorentzian wormholes from other types is that they exist in real time, not in some mathematical abstraction, but in the same spacetime fabric that everything else occupies. And this is where the most unsettling implication arises. In 1988, Morris, Thorne, and Yurtsever published a companion paper in Physical Review Letters showing that a traversable Lorentzian wormhole could be converted into a time machine. The mechanism requires only that one mouth of the wormhole be accelerated to near the speed of light and then returned to its original position. Special relativity predicts that the accelerated mouth ages more slowly than the stationary one. Time dilation. After the acceleration phase, the two mouths exist at different points in time relative to each other, even though they remain connected through the wormhole interior. An object entering the younger mouth would emerge from the older one in the past. This is not science fiction. It is a direct consequence of combining the physics of traversable wormholes with special relativistic time dilation. Kip Thorne, who received the Nobel Prize in Physics in 2017 for his role in detecting gravitational waves, is one of the physicists who worked through this mathematics in detail. His conclusion was not that time travel through wormholes is possible, but that if traversable wormholes exist, the physics that prevents time travel paradoxes must come from somewhere outside general relativity. Either quantum effects destroy the wormhole before the time machine can be completed, or the universe has some other mechanism, not yet identified, for enforcing causality. 4. The Euclidean wormhole. The one that exists in imaginary time. Not all wormholes live in the spacetime of everyday physics. Euclidean wormholes exist in Euclidean spacetime, a mathematical framework used in quantum gravity and quantum field theory, where time is replaced by an imaginary variable. This is not a philosophical maneuver. It is a technical tool called a Wick rotation, in which the time coordinate is multiplied by the square root of -1. The resulting mathematics becomes much more tractable for certain calculations, and the solutions found in Euclidean spacetime can often be rotated back to give predictions about the real Lorentzian universe. In Euclidean spacetime, wormhole solutions called instantons appear. These are saddle point contributions to quantum gravity path integrals, mathematical entities that represent the universe tunneling through a topological change. Euclidean wormholes do not connect two spatial regions for travelers to cross. They represent the possibility that the topology of spacetime itself fluctuates, that spacetime can spontaneously develop connections between distant regions at the quantum level and then lose them again. Stephen Hawking and others proposed that Euclidean wormholes might affect fundamental physical constants, that the quantum fluctuations in spacetime topology they represent could contribute to determining why the cosmological constant is the value it is, or why the masses of particles are what they are. This remains speculative. Euclidean wormholes are a calculational tool and a theoretical framework. They do not appear in any direct observational context, but they emerge from the most serious attempts to construct a quantum theory of gravity, and physicists take them seriously in that context. 5. The inter-universe wormhole. The door to somewhere that is not here. The Einstein-Rosen bridge, in its original formulation, connects not two distant points in the same universe but two entirely separate universes, two disconnected regions of spacetime with no other causal connection. The inter-universe wormhole is a generalization of this concept in modern cosmological frameworks. In eternal inflation, the theoretical process by which the inflationary epoch of the Big Bang produces a vast landscape of separate bubble universes, each with its own physical constants and laws. The individual bubble universes are causally disconnected from each other. No signal can travel between them through ordinary spacetime. A wormhole connecting two such bubble universes would be a topological bridge between realities that have no other physical relationship. It would not be a shortcut through our universe. It would be a door to a place that is not our universe at all, in any sense. A region of spacetime with potentially different particle masses, different forces, different cosmological constants, and no prior causal connection to anything we have ever observed. Whether such wormholes could form, or could be stable if they did, depends on the full theory of quantum gravity, which we do not have. In the framework of string theory and the string landscape, inter-universe connections of various kinds are theoretically discussed. No mechanism for their formation from within our universe is currently known. 6. The quantum wormhole. The tunnel between entangled particles. In 2013, physicists Juan Maldacena and Leonard Susskind published a short paper proposing one of the most radical ideas in modern theoretical physics. They called it ER equals EPR. ER stands for Einstein-Rosen, the wormhole. EPR stands for Einstein-Podolsky-Rosen, the 1935 paper that introduced quantum entanglement, the phenomenon by which two particles remain correlated regardless of the distance between them, so that measuring one instantly affects the state of the other. Maldacena and Susskind proposed that these two phenomena, wormholes and entanglement, are not separate things. They are the same thing, described in two different languages. Every pair of entangled particles is connected by a non-traversable Einstein-Rosen bridge. The entanglement is the wormhole. This is not a metaphor. It is a precise mathematical conjecture with calculable consequences. The two maximally entangled black holes in the eternal Schwarzschild solution, the original Einstein-Rosen bridge, are in a quantum state called the thermofield double state, which is a maximally entangled state. The geometry and the entanglement describe the same physical reality. If ER equals EPR is correct, then wormholes are not exotic astronomical objects that might or might not exist somewhere in the universe. Every entangled electron pair, every photon pair produced in quantum optics experiments, every qubit in a quantum computer, all of them are connected by microscopic, non-traversable wormholes right now, everywhere, in every laboratory on Earth. The wormhole is already there. It just cannot be used to send anything through it. The non-traversability of the quantum wormhole is, in this framework, the reason entanglement cannot be used to send information faster than light. A limitation that has been experimentally confirmed many thousands of times. 7. The Casimir wormhole. Powered by nothing. The Casimir effect produces negative energy density in the gap between two parallel conducting plates. This is experimentally real. It has been measured. The negative energy density is small, measurable only at separations of micrometers or less. But it is genuine negative energy density, the same mathematical property that Morris and Thorne identified as required to hold a wormhole throat open. Casimir wormholes are a class of traversable wormhole solutions in which the exotic matter holding the throat open is specifically the negative energy density of the quantum vacuum, the same Casimir energy observed in laboratory experiments. Physicists, including Kuhnel and Reidel, and more recently groups working in modified gravity theories, have constructed explicit mathematical solutions for wormhole geometries sourced by Casimir energy. The solutions are mathematically valid. The physics of the source is experimentally real. The problem is scale. The Casimir effect at laboratory scales produces negative energy densities of approximately 10 to the negative 3 joules per cubic meter at plate separations of 1 micrometer. A traversable wormhole of any macroscopic size would require negative energy densities many orders of magnitude greater, sustained over a macroscopic volume. No mechanism is known for generating Casimir-type negative energy at this scale. The Casimir wormhole is the closest contact between experimentally verified physics and traversable wormhole theory. It is a real solution, sourced by a real effect. The engineering gap between the two remains, for now, unbridgeable. 8. The Planck scale wormhole. The foam beneath spacetime. At the smallest scale that physics can describe, the Planck length, approximately 1.6 times 10 to the negative 35 meters, spacetime is not smooth. John Wheeler proposed in 1955 that at this scale, quantum fluctuations in the geometry of spacetime become so violent that the very topology of space changes rapidly and continuously. He called this spacetime foam. In spacetime foam, wormhole connections between different regions are constantly forming and collapsing at the Planck scale, trillions of times per second, at a scale so small that no known force or particle can interact with them directly. These Planck-scale wormholes are not shortcuts in any practical sense. They are too small by approximately 20 orders of magnitude for any particle in the Standard Model to enter. But they represent the universe's most fundamental texture, a seething quantum structure beneath the smooth spacetime of everyday physics, in which connectivity itself is constantly in flux. Whether spacetime foam exists in the form Wheeler described remains unconfirmed. At the Planck scale, neither general relativity nor quantum field theory applies independently, and the theory of quantum gravity needed to describe this regime does not yet exist. The foam is a prediction of taking both theories seriously at their limits simultaneously. It may be that the universe, at its smallest scale, is not a smooth, continuous fabric at all. It may be a constantly shifting network of microscopic connections, wormholes so small they are invisible to everything we can currently measure, threading through the structure of spacetime itself. The concept of a wormhole began as an unexpected solution to equations that were supposed to be describing something else entirely. 90 years later, it has expanded from a mathematical curiosity into a framework that connects the largest structures in cosmology, the topology of separate universes, to the smallest, the entanglement of individual particles. Every type described here emerges from the same source, the equations of general relativity and quantum mechanics, pushed to their limits and taken seriously. The Einstein-Rosen bridge collapses before anything crosses it. The Morris-Thorne wormhole stays open but requires matter that may not exist. The Lorentzian wormhole implies time travel if it can be built. The Euclidean wormhole exists only in imaginary time. The inter-universe wormhole leads somewhere that is not here. The quantum wormhole connects every entangled particle in the universe right now. The Casimir wormhole is sourced by an effect you can measure in a laboratory. The Planck-scale wormhole may be part of the fabric of spacetime itself. None of them have been observed directly. All of them are permitted by physics. The universe keeps producing these solutions. The honest question is not whether wormholes exist. It is why the equations keep insisting that they should.